Good morning. It's good to be connected live with you, sitting here, standing here in America and talking to you in India. It has been a privilege giving you some insight about the latest development in energy field. The topic which I have chosen today to deliver is based upon solar thermal storage for sustainable energy generation. So I'll go one by one on some of the words which I have used here, explaining the title. So the solar comes from sun, and thermal means using solar energy in the form of heat to generate electricity. And then is the sustainable energy generation. The word sustainable has a specific meaning. The word sustainable here means meeting your need, meeting the need of your energy without compromising the ability of the future generation to meet their need. So this building here, which you are seeing, is a very beautiful building. That's where I work. This is Florida Polytechnic, IST building, Innovation, Science and Technology building. It recently won an international award for the building design. It's in one of the most energy efficient building I have worked in. If you see this building carefully, it's kind of a wing structure which you are seeing. It has a movable roof. So this movable roof allows direct sunlight, the natural sunlight, to come inside the building. So you don't, during the daytime, you don't need artificial lighting. So you save a lot of energy in there. This college, this university was set up quite recently. In fact, we had the first class in 2014, and it caters to different STEM education field, science, technology, engineering, and mathematics. Courses running from engineering field, nanotechnology, multifunctional materials, cyber gaming, cyber security. So this building here was designed by Dr. Santiago Calatrava. He's the guy who designed also the World Trade Center. Coming to the topic, most of the nations in this world, in fact everyone, the human race is looking to progress. The main object is the progress of the human race, and not only the human race, progress of the animals who live with us, progress of not only the animals who are living with us, domesticated one, but also in the world. So it's not the progress of only us, it's the progress of all of us living on the planet Earth. But now it's not only progress, but also the sustainable progress. So I already explained sustainable. Sustainable means doing something to meet our needs without affecting the efficiency of the future generation. So that's very critical. To get to the sustainable progress, what we need an efficient power generation. And how we are doing it? We are generating energy by burning fossil fuels. Now, as we all know, fossil fuel generates a lot of pollution, and that's how we are killing our Mother Earth. That's how we are polluting our environment. That's how we are affecting the future generation. So this is not sustainable. So what we want to do, we want to generate efficient energy and efficient power generation, but by keeping our environment clean, by keeping our earth green. So that's the objective of now, the objective of the research now being carried out as far as the energy generation is concerned. So what is the solution for that? That how we can generate an efficient energy without affecting our environment is by using the renewable energy resources. Renewable energy resources like the solar energy, the wind energy, the geothermal energy. And if you consider the renewable and if you just consider the solar energy, it's abundantly available. The amount of energy which we get from sun in a single year is around about 8,000 times more than the amount of energy we will get if we burn all the energy resources, all the non-renewable energy resources at one time. So this is the power of solar alone, that the amount of energy is huge. So it's abundantly available. Then what is the problem? Why we are not using it? One of the problem is that the renewable energy resources are intermittent in nature. Means, I'll again go back. You have sun, you can generate electricity using two different technologies are there. I'm going to talk about that. But the moment the sun goes out, it may be due to the appearance of cloud on a rainy day or something, you stop generating electricity. So the intermittent nature is the biggest hurdle in applying the renewable energy resources for meeting our energy needs. The other problem is the diffused nature. The surface temperature of sun is around about 5,000 degrees Celsius. So it's that high, and the temperature on the earth is around about 15 degrees C. So the temperature on the earth is not that great. So we cannot use, so it's so diffused that we cannot use it directly to convert that into a useful energy so that we can generate electricity. So that's the other problem, that the sunlight is diffused. So there are two different technologies which is used to generate electricity from the solar energy. The first technology, which is more prevalent, it's most common in there, and it's highly implemented, is the photovoltaic technology, the PV technology. In this technology, the solar energy is used, the radiation from the solar energy that interacts with the solar cells, and the solar cells based upon the photoelectron effect generates the electricity, and the electricity which is generated is in the DC form. It's a direct current. So the next step in this technology is convert that DC current into an AC, and also for supplying it to the grid, the voltage which we get from the solar panels needs to be jacked up. In one of the solar power plant which I visited, the voltage which was generated was close to like 600 volts, but when it was transmitted to a power grid, the voltage needs to be jacked up from 600 to around about 12,000 volts. So this is the photovoltaic technology. The other technology which is being used and is relatively new as compared to, in terms of being implemented on a commercial scale as compared to the photovoltaic, is the concentrated solar power plants. So concentrated solar power plants has entirely a different mechanism of using solar energy to generate the electricity. In a concentrated solar power plants, you will see there are two different images which I have provided to you. One, there are two on the top, which is called the parabolic troughs. It's a concentrated solar power plant based upon the parabolic trough, and the one which is at the bottom, which you're seeing, is the central receiver power plant. The concentrated solar power plants use the solar energy and convert that solar energy into a heat, and that heat is used to heat the heat transfer fluid. So if you just see the other diagram here, in between the just in the middle of the parabolic trough, this is just like this one, the trace, the parabolic trough, there is this tube which is passing through it. The tube contains an heat transfer fluid. There are different heat transfer fluids which are now being used. There is an oil which is a biphenyl oxide. It's a kind of a polymeric structure, and it's an oil. It's normally used as a heat transfer fluid for the parabolic type concentrated solar power plants. Water is another for very low temperature concentrated solar power plants. People are thinking of using water as a heat transfer fluid. Air is another one which can be used as a heat transfer fluid, but the specific heat is so low, so people are not using air at low temperature as a heat transfer fluid, but at high temperature air could be used as a heat transfer fluid. So during daytime, the sun is used to heat the heat transfer fluid. So what happens is the rays falls on this parabolic trough, and they are oriented in such a way that the rays are concentrated on this tube, and as a result they heat the heat transfer fluid to a certain temperature. The parabolic trough is around about somewhere between 300 degrees C to around about 580 degrees C. That's the temperature they are going up to. And then also the temperature of the parabolic trough depends upon the heat transfer fluid which is being used. If oil is used as a heat transfer fluid, then they are going around about 400 degrees C. If they are using molten salt as a heat transfer fluid, then they are going around about 580 degrees C. But the limitation of the parabolic trough is that it cannot go beyond that temperature. The other technology which is coming up and which can give us higher temperature than the parabolic trough is the central power receiver. In the central power receiver, the basic phenomena, the basic principle is same, that you concentrate the sunlight which falls on the mirror to a point where it heats the heat transfer fluid to a certain temperature. In this case, instead of a parabolic trough, instead of having a curvature kind of a mirror, it has the plane mirrors. And these mirrors are called the heliostat. And as you can see from this diagram, the rays which are falling on the mirror are reflected to a point on the tower which contains the heat transfer fluid. The way it happens is, with this technology, you can heat it to a much higher temperature than what you can achieve with the parabolic trough, so probably 600, 700, or even say 800 degrees C. So that's what the central power receiver can do. It can provide you higher temperature. So as I said, the technologies are there to use solar energy to generate electricity. But the biggest problem with the solar energy is its intermittent nature, and also it makes it unpredictable. To integrate all the solar power plants to the grid, the reliability is one of the biggest issue. The grid needs to know that how much energy is getting at what time, and there shouldn't be much of a fluctuation in the availability of the energy. So intermittent nature is the biggest hurdle in successfully integrating the solar power plants on a great scale. On a smaller scale, not that a problem. So how do we solve that problem? So the intermittent nature of solar energy can be solved by a technology which we say the energy storage technologies. Now, what is energy storage? So before I go with the energy storage, let's talk about the storage. What is storage? A very simple example. There are times when we generate a lot of food. Say, for example, wheat, we grow wheat, and in the month of April, that's the time when we are harvesting wheat. So what we do? We generate a lot of heat, a lot of wheat, a lot of food at that time, which is not consumed at that time. So what we do? We store it in warehouses, and whenever the need arises, we take that food out from the warehouses and distribute it in the open market so that people can consume. So when food is available in plentiful, that's the time when we are storing, and when it's needed, that's the time when we take it out and distribute it to the people so that they can consume. And the same concept goes for the energy storage, that when the energy is available during the daytime, when the sun is out, when it is available in abundance, part of that energy we use directly to generate electricity, but a part of that energy we store it to use it at a time when the sun is not available, maybe during a rainy day, maybe during, say, all of a sudden a cloud cover comes over the sun, and also during the night time. See here, the direct computation of the solar energy or the renewable is with the non-renewable resources. The biggest advantage with the non-renewable resources is the reliability. We can generate energy from the non-renewable 24 hours. We can predict how much energy could be generated from a certain thermal power plant, and a certain amount of electricity could be provided to the grid. So it's very, very reliable, and it's also available 24 hours. So in order for the non-renewables to compete directly with the non-renewables, then the reliability has to increase. The availability has to increase. Not sun is available for say 8 hours or 9 hours at most, then what happens for the 16 hours or the 15 hours? So you need to do something so that the sun is available 24 hours. So the only way to do that is by an energy storage technology. In energy storage technology, as I have explained, that you store a part of the solar energy during the daytime in certain form and use it to generate electricity when sun is not available. So energy storage can be accomplished by 3 different means. I have broadly categorized them into 3 categories. So there are 3 categories. The first category is the mechanical energy storage. The second is the electrochemical energy storage, and third is the thermal energy storage, which is the part of my lecture today. The discussion is on the thermal energy storage. Now, what is mechanical energy storage? The mechanical energy storage is storing the energy in the form of kinetic energy, in the form of some kind of emotion. In India, I was recently reading that on a large scale they are trying to implement, they are trying to generate electricity from the solar, and according to one estimate, they want to generate around about 500 gigawatt. Now that's a lot of solar energy by putting solar panels on the wasteland. So this is their estimate. The biggest problem with there will come about the intermittent nature. The biggest challenge will come about the energy storage. Where the research is going, where the currently they are looking into is the mechanical energy storage. And in mechanical energy storage, they are looking at the technology which is called the hydro pumped storage. Now, what is an hydro pumped storage? Hydro pumped storage is just very similar to to the dam way of generating electricity. The hydro generation, where we store water in big lakes, and then the water is allowed to fall from a certain height, and it falls on the turbines. The turbines are rotated, and that's how they generate electricity. So that's what the same phenomena is with the hydro pump storage. In the hydro pump storage, what they're looking at is 2 large reservoirs. One reservoir at low elevation, whereas the other one at higher elevation. So there are 2 different water bodies at 2 different elevations. So during daytime, or during the time when the electricity is available in abundance, but the consumption is not that high. Normally what the power plant, the thermal power plants or the other power plants do is, during the time when the demand is low and the generation is high, they curtail that generation. That's what they have been doing. But in case of if you have an efficient storage technology available, then you need not curtail the energy generation, because every time you curtail the energy generation and then jack up when the power demands rises, then you are compromising on the efficiency. And when you're compromising on the efficiency, you're generating more pollution, you need more power plants set up, so that creates a lot of problems. So energy storage solves that problem. So I come back to that. When the electricity is generated in large amount and the consumption is not that high during that time, that electricity generated is used to pump water from the low reservoir to a high reservoir. So the electricity is used to pump water from a low reservoir to a high reservoir. And when the demand rises and the generation can't keep up, at that time the water is allowed to fall freely from the higher reservoir into the lower reservoir. So in between you will see there is a turbine, a reversible turbine. So the water, when hits that reversible turbine, it generates the electricity the same way as a hydroelectric dam generates the electricity. The same principle, so there is not much of a difference. The only difference is that when electricity is available in abundance, you use that to pump water to a higher level, and when you need electricity back, you allow the water from the higher reservoir to fall down into the lower reservoir, and in that process generate electricity. This is one of the efficient way, in fact the most efficient way of storing energy and also generating electricity from it. Then what is the problem? The problem is same as of an hydroelectric dam. You need a large area. You cannot build that hydroelectric dam everywhere. Means there has to be a certain geographical parameters, certain geographical features which are needed to build kind of a hydroelectric dam, and same is with a hydro pump storage. You need an area where there is a natural elevation available so that you have a high reservoir and a low reservoir. The other problem is, since so gigantic, it's so big in size that it affects the natural flora and fauna, so it affects the ecosystem around. So that's the other problem. The third problem is the induction time. To build this kind of a facility, it takes a lot of time. It takes around about 3 to 4 years to set up this kind of a facility. So all these things makes this hydro pump storage not that attractive if you're looking for some quick solution. But as far as the energy efficiency is concerned, zero emission, this is a very, very wonderful technology. So what are the other options? The other option is storing energy in the form of electrochemical energy. Now electrochemical energy is storing energy in batteries. This is what we have been doing in our home. So all of our home has the batteries and the inverters. So whenever there is a power outage, whenever there is a power cut, the energy, the electricity which is stored in the battery is used through an inverter to run our appliances, be it a refrigerator or some fan or the lights. So we have been using this technology in our home on a very small scale. For a photovoltaic, this is one of the way of storing energy. Photovoltaic generate electricity, and that's a direct current, and you can store that in the batteries. But here also, one of the issues with the batteries is the cost, the reliability. One of the most efficient batteries are the lithium-ion batteries, but those are very expensive. So, and also if you want to implement that on a large scale, on a great scale, you need a large number of batteries. So that's where the development is in the electrochemical energy storage, is to bring down the cost of the batteries so that you can implement it on large scale and store energy for generation at a time when the renewables are not available. The third way of storing solar energy is the thermal energy storage. Now what is thermal energy storage? As the name suggests, thermal. Thermal means heat. So storing energy in the form of heat, that is the thermal energy storage, and that is what the topic of my talk and also my research is on thermal energy storage. Now thermal energy storage can also be accomplished in 3 different ways. So the 3 different ways is, one is a sensible thermal energy storage, the second is the latent thermal energy storage, and the third is thermochemical energy storage. The technology which is now being used on a very large scale, in fact there is one big concentrated solar power plants in Arizona, it's the Solana concentrated solar power plants is using the sensible energy storage to store solar energy during daytime and use it at night time to generate electricity. Even in India, there are a couple of power plants. One of them is in Rajasthan, which is using the sensible energy storage to store energy, to store solar energy to be used at a later time when sun is not available. So what is done in a sensible energy storage? In sensible energy storage, this is just like heating an object to a certain temperature and utilizing the specific heat of that object to store the energy. So in sensible, the various materials which are used to store, or various storage materials, are the rocks, the salt, and the oil. And as I said, you use solar energy to heat this object to a certain temperature, so these objects are heated, say for example from the room temperature to 500 degrees C or 580 degrees C, and you keep this storage material in big tanks, and those big tanks are well insulated, so there is not much of an heat loss. And when you need this energy back, when you need to generate electricity, you allow the heat transfer fluid to pass through this tank and get all the heat which is stored in this material out, and then it goes to the power block where it generates the electricity. I'll come back to that. The second type of thermal energy storage is the latent heat. Latent means hidden, and that's what I have been doing. My current research is on latent heat storage. In latent heat storage, we use this specific kind of materials which we call the phase change materials. Now, what are these phase change materials? What do you mean by phase change material? We can heat an object to a certain temperature, and we can heat an object to a temperature where it changes its phase. Now, phase means we can heat an object where it gets converted from solid to liquid, or if we start from a liquid gets converted into a gas. So that's a phase change from solid to liquid or liquid to gas. So we are going to use in latent heat energy storage the materials which changes phase on heating. The example is wax. Say you have wax as a storage material. You heat wax to a temperature where all the wax melts. Water is another. You heat liquid water to a temperature where it gets converted into vapors. So that's a latent heat of vaporization. What is the advantage of latent heat then compared to the sensible? The advantage is latent heat energy storage material has higher energy storage density. What I talked about, the latent heat of vaporization, the latent heat is the hidden heat. It's the heat which is available when a material changes its phase. So when I compare the sensible energy storage material with the phase change material, it is around about 4 to 5 times higher energy storage density than the sensible heat storage. Then the question comes, why we are not using it? Why we are not using it? We are not using it because there are certain issues with the latent heat energy storage, and we are going to talk about that. So let me here compare the sensible heat storage versus latent heat storage. And as I said, the sensible heat storage is a fully commercialized technology. It's being implemented. So on the left hand side, this diagram represents a energy storage system integrated successfully with the solar power plant. So what you see here is there is a solar field, and you can see here it's a parabolic trough, and then there are 2 storage tanks here which are used to store the solar energy in the form of heat when the sun is available. And on the other side, you'll see this is the power block. This is the system which uses the heat to generate electricity, and it's not much different from the thermal energy from the thermal power plants. They have the power block, which looks almost similar to what concentrated solar power plants use. So that's the advantage of thermal energy storage, that you can integrate the thermal energy storage with any kind of power plants, be it be a conventional thermal power plants. That's the advantage of the concentrated solar power plants. You can have a concentrated solar power plant and a normal thermal coal run or a fossil fuel run thermal power plants at the same time. So during daytime you can use the concentrated solar power plant. During nighttime you can use the conventional power plant. So it can augment, both can augment each other. So that's an advantage. That's the advantage which is not there in the PV technologies. So during daytime, when sun is available, the parabolic trough is used to heat the heat transfer fluid. So as you can see in this diagram, during daytime, the red portion here represents the heat transfer fluid at higher temperature. So part of that heat transfer fluid directly goes to the power block and generate electricity, which can be distributed on larger scale. But a part of heat transfer fluid goes through, this is here is an heat exchanger, so goes through an heat exchanger. Now what happens at the heat exchanger is that the storage material, this is a molten salt here, salt in a molten state. A storage material which is a molten salt is pumped and it comes to the heat exchanger, where the heat transfer fluid and the the storage material exchange their heat. As a result, the heat transfer fluid cools down, whereas the molten salt heats up. So you can see there is a red in there, and that heated molten salt goes to another tank, which is called the hot storage tank. And this technology is called the two-tank molten salt technology, the molten salt storage technology. And during nighttime, when sun is not available, the whole process reverses. What happens is, during nighttime, the heat transfer fluid at lower temperature comes to the heat exchanger, and the hot molten salt, which is probably at 500 or 580 degrees C or say 400 degrees C, comes at this point. Now the heat flow is in opposite direction. So heat flows from the molten salt into the heat transfer fluid. So as a result, during night time is the heat transfer fluid which is being heated, and whereas the molten salt is getting at lower temperature. So what happens is the heat transfer fluid at lower temperature then comes back to the cold storage tank, and then the heat transfer fluid goes to the power block and generates the electricity in a normal way. So this is the sensible way. Now, in this kind of storage system, the amount of energy stored is given up. It's a normal thermochemical. That's where the chemistry comes into picture, as the mass of the storage material times the CP, the specific heat of that storage material, and the temperature difference. So higher is the temperature difference, more is the heat stored. Higher is the specific heat of the material, higher is the energy storage density, but this is sensible. The other problem, in addition to low energy storage density, the other problem with this technology is it's dealing with molten salts. Now molten salts, the molten inorganic salts, those are currently the salt which is being used is a mixture of sodium nitrate. It's a eutectic mixture of sodium nitrate and potassium nitrate, which has a melting point of around about 225 degrees C. So salt, inorganic salt in molten states are highly corrosive, and we're talking about pumping the molten salt from one storage tank into another. So a lot of corrosion may happen. So that's the other problem with this technology. So low energy density and the corrosion. What advantage we get with the phase change material? As I said earlier, with the phase change material, with the latent heat energy storage density, we get a higher energy density, because in latent heat energy storage, we not only get the storage because of the specific heat, we also get the storage because of the heat of fusion, because of the heat involved during the phase change. If I'm talking about from solid to liquid, then it's a heat of fusion. And if I'm talking about it's also called the latent heat, but if I'm talking about from liquid to gas, then it's latent heat of vaporization, and those are really, really high. So in latent heat energy storage material, you not only get the specific heat energy storage, so this is like the sensible, this part is sensible, that part is again sensible. So this is sensible in the solid state, this is sensible in the liquid state, and in between that you have that latent heat energy storage, the delta H, and this is what it provides higher energy from the sensible. Now the other advantage with this technology is that instead of using 2 tanks, you just need to use 1 tank. And so what you see is you have the solar field, so the heat transfer fluid during the daytime goes directly and produces the electricity, and some part of that heat transfer fluid goes into the storage tank. So it directly goes into the storage tank. There is no need as far as the heat exchange is concerned, there is no need for an heat exchanger. So this is completely eliminated. So it's not only about an additional equipment or an additional step, but it's also about the efficiency. So it's the better way of transferring heat from one system into another. So heat transfer fluid directly goes into the storage tank, and when it comes at a lower temperature, and then it again goes back to the solar field. So this happens during the daytime. During nighttime, the heat transfer fluid at lower temperature, which comes from the power block, goes into the storage tank and passes through the phase change material, and there is a reverse flow of heat now. The heat is being transferred from the phase change material into the heat transfer fluid, and that heat transfer fluid goes to the power block, and you get electricity during nighttime. Advantages are tremendous. Higher energy storage density. Second is corrosion. This is less corrosion. This is the tendency of this material to corrode is less as compared to the molten salts. But if this technology has so many advantages, what are the problems? The problem is low thermal conductivity of the phase change materials. Now, remember, there are 2 things which are happening in energy storage. One we call the charging. That's during daytime when you're storing heat in the storage material, and during nighttime we call it discharging, that when you need that heat back to generate electricity. So there is a charging of the system and there is a discharging of the system. And in both these cases, the phenomena which is involved is the heat transfer. During charging, the heat is being transferred from the heat transfer fluid into the phase change material, and during discharging, the heat is being transferred from the phase change material into heat transfer fluid. So there is a transfer of heat. So that's why the conductivity plays such a huge role. So if your material has very low thermal conductivity, then the rate of heat transfer between these things, heat transfer fluid and the phase change material, becomes really, really slow. And there is a sudden jump in the electricity demand. So you need electricity immediately. You need to jack up the generation of electricity as soon as possible. But if the conductivity is low, you cannot do it. Now that's the biggest concern with the phase change material. So how to alleviate this problem, how to remove this problem? One way people have been trying is that in this phase change material, they add some conductive particles like small metal particles, small nanoparticles, carbon particles, graphite, and all those things. They are using metal mesh to increase the conductivity. But all those has certain issues, like in the particles, there is a density difference between the phase change material and the higher conducting particles which you are adding. So what happens is, because of the energy difference, those particles either float in the phase change material when they are in molten state, or they just settle down. And there are some other issues too. The other way of increasing the thermal conductivity of the phase change material is by a technique which is called micro or macro encapsulation of PCM. That means instead of filling a huge tank with phase change material, you fill it with the phase change material which has been encapsulated. So that means you prepare the capsules of the phase change material and dump that into the storage tank. So these are, you can see there are two capsules, two small sizes, around about an inch of a diameter. So what you have done, so this example is similar. If I take a very big log of wood and try to burn it, it will be very difficult to burn it. But if I take a very small pieces of those wood and try to burn it, it will be much easier. So what I have done, I have increased the surface area. So whenever you increase the surface area, it becomes easier to initiate the reaction. It becomes easier to speed up the reaction. So that's what the idea behind it, that instead of having a large amount of phase change material dumped into a single storage tank, why not have them encapsulated into small capsules, and then the heat transfer fluid can flow through these capsules and the heat can be directly transferred from these capsules into the heat transfer fluid. So encapsulation is one of the way of increasing the thermal conductivity of the PCM by increasing the surface area. What is the problem? How we can accomplish the encapsulation of phase change material? So what we have done, we have grouped those barriers of encapsulating a phase change material into two categories. The one we call a physical barrier and the other is called the chemical barrier. Now what is a physical barrier? A physical barrier is when PCM is in solid state and you start heating it up, as you heat up the material, the density goes on decreasing. And this is because the volume starts increasing. This happens with most of the material. Water is a little bit opposite. This happens with most of the material. The density decreases and starts to expand. As they are in solid state, the expansion is not that great. But phase change material, we are going from one phase to another. We are going from solid to liquid. When that happens, when a solid gets converted to a liquid, there is a huge expansion of the volume and decrease in density. So the material expands. So when the material is going to expand, and if you have a kind of a rigid encapsulation inside, then it's going to generate pressure inside the capsule. And if this pressure inside the capsule is stronger, is higher than the strength of the encapsulating material, then what's going to happen is it's going to explode. It's going to, the coating is going to crack. So this is the physical barrier. The other thing is, when you're encapsulating a solid, no matter how closely you pack them, hexagonal close packing, there still be some pores left in there. And that pore, that voids will contain air. And so when you're heating the capsules with the heat transfer fluid, not only the phase change material which is expanding, but also the air is going to expand. According to one estimate, if you're encapsulating a material at room temperature and you're heating it up to like 800 degrees C, the pressure inside the capsule becomes 25 times. So that increases from 1 atmospheric pressure, it becomes 25 atmospheric pressure. Now that's a very high pressure. So how to contain that pressure? You cannot increase, or you should not increase the thickness of the coating, because then that increases the cost, that increases the width, that increases the thickness of the coating as compared to PCM, so that decreases the rate of heat transfer. So you want your thickness of your coating as thin as possible. The second category for successfully encapsulating, which act as a barrier, is called the chemical barrier. In chemical barrier is the reaction of the phase change material with the coating. Now in most of the cases at high temperature, I'm talking about high temperature 300, 400, 500 or even 800 degrees C, the material which is used to store energy, the material which is used as a phase change material are inorganic salts, and the inorganic salts again in the molten state are very corrosive. So your coating materials should not react with the molten salt. So how did we solve this problem? So we successfully solved this problem. We have filed a patent on it. A paper has been published in one of the topmost journal in energy field. It's applied energy, and we solved this problem through a very innovative way of encapsulating the phase change material. And that's how what I mean that it's a perfect blend of a theory and an experiment, that you build certain model in your mind, and based upon your model you carry out certain experiments, and at the end you get a successful result from it. So the model which was developed to encapsulate this phase change material was that the PCM will be encapsulated with a polymer. Now this polymer, the advantage of the polymer is because it is a polymer, it can expand when you heat it up. So it is flexible. A polymer is flexible in nature. So we wanted to choose a polymer which is flexible. So as you heat the material, as the phase change material expands, as the air inside the capsule expands, so does the polymer outside the phase change material. So having a flexible polymer outside the phase change material solved our first problem of the physical barrier of what happens when the solid is going to expand, when the solid is going to get converted into liquid, as you take a polymer which expands along with the material. And this is just like a balloon. When you fill balloon with the air, so as you put more and more air into the balloon, it just expands. So that was the first thing which we thought of. The second physical barrier is what is going to happen with the pressure. As you can see, if you keep on inflating balloon with air, there will come a time when it going to burst up. So the same problem is our problem, that when you're heating the material and the air inside is the capsule, so the air is going to expand, it's going to create some pressure. According to one estimate, as I said, the pressure could be 25 times to the original pressure, from 1 atmospheric pressure to 25 atmospheric pressure. So the idea here is to develop a coating which is selectively permeable. That means when I say selectively permeable, it allows the air to diffuse out, but it doesn't allow the molten salt to go out through those pores. And the polymers, there are some polymers available which has those inherent pores, those microscopic or nanoscale pores inside the polymers, which can allow the air to diffuse out. But since those molten salts are larger molecules and the ions are larger, they cannot pass through those pores. So get a polymer which is selectively permeable. So we solve that problem by using a polymer which is flexible and also selectively permeable. So once we do that, the third issue comes into picture, that will it react? What is the compatibility of the polymer with the molten salt? To see that, we did some experiment. This is a graph depicting the compatibility of different materials which we tested. These are mostly the polymers, compatibility of the different polymers in the presence of the phase change material which we are using to encapsulate, which we are using to store solar energy in the form of heat. Now this is a TGA graph, thermogrammatical graph. So what we done is that we took the polymer and had that dipped into or mixed it in with the molten salts, and we heated it to a certain temperature, and we saw that in the absence of salt, what is the temperature where the polymer decomposed, and when the salt is present, what is the decomposition temperature. As you can see, I can give you an example here. If you see this purple line here, in the absence of salt, the polymer decomposed around about 570 degrees C, but in the presence of the phase change material, in the presence of the salt which we plan to use, the decomposition started at 465 degrees C. So, the decomposition has come even down from like close to 105 degrees C. So, this clearly indicates that the molten salt is reacting with this polymer. So, we cannot use this polymer for encapsulating this material. But you can see another material here, the green one, the one with the solid lines and the other with the dotted lines. It's the same polymer, and the TJ was run with and without the molten salt. And as you can see, in both the cases, the decomposition temperature remains same. So, it's around about 535 degrees C. So, the decomposition temperature didn't change. So, that means that this polymer didn't react with the molten salt. So, we said, okay, this is the material which we can use to encapsulate the phase change material. But that's not all. As I said, this is a technology. This is a technology which goes into the market. This is a technology which will have a shelf life for around about 20 years or 30 years. So, once a capsule is made, it has to survive those 20 years or 30 years of that cycle. So, you need to make sure that the material which you have chosen can maintain its integrate over an extended period of time. So, we did another experiment which is called the isothermal TGA. So, we studied different materials in the presence of salt and kept it at a certain temperature for a very long period of time. So, again we wanted to see, do we see any kind of decomposition, any kind of a reaction between the encapsulating material and the phase change material. So, as you can see between these two lines, when we kept it at a certain temperature at around about 326 degrees C, you can see there are two materials which showed some weight loss. So, there is a weight loss. So, that clearly told us that there is some kind of a reaction which is going on with the phase change material and the selected material. The other material which we selected here, the green one, for some proprietary reason, I am not going to tell which material which we used it. So, the green here, as you can see, over a very extended period of time, it didn't show any weight loss. So, that means it's perfectly compatible with the phase change material. So, that's how we solved the chemical problem. So, we solved the physical problem by selecting polymers which is flexible and selectively permeable, and we solved the chemical barrier by carrying a certain compatibility studies involving thermogrammatical analysis, where we selected a material which didn't show any reactivity with the chosen phase change material. So, this is the process which we developed, and it's highly successful. We started from the powder PCM, which is the phase change material. We converted that into the solid hemispherical or spherical balls. So, this is spherical and this is hemispherical, and then we coated it with a polymer. Now, the polymer is flexible, the polymer is selectively permeable, but it does not have the strength. You are going to put this capsules into large storage tank, and according to one of the estimate, it could be like 1 million capsules in a single tank. So, you can imagine all these capsules sitting one over the other. So, there will be a huge pressure which these mechanical pressure which these capsules need to bear while they are inside the tank. So, there has to be some strength which is to be provided. So, to provide strength to the capsules, we thought of metallizing these capsules. So, what you see here is the capsules coated with the polymer has been metallized. The process which we developed to metallize these capsules is again a state-of-art process. We invented this process of metallizing. There has to be some unique features in this metallization. But broadly, the technique which we used is there, available in the market, is the electroless deposition and the electrolytic plating. What is electroless deposition? It's a simple redox chemistry reactions where you use a solution containing metal ions and then you reduce it with a reducing agent so that metal ion gets converted into metals. So when you do that reaction on small molecular scale or ionic scale, you will have very small particles of metal deposited on the substrate, and that's the reason you get a very good coating of the metal. The issue with the electroless deposition is you cannot build thickness. So in order to build thickness, the technique which was used to put more metal on this capsule was the electrolytic plating. In electrolytic plating is electrochemistry, you must be knowing about it. There is a cathode and an anode, and so cathode and anode electricity current, the current is passed through it, and there is a deposition on the cathode, and there is an oxidation which is occurring at the anode. So the electrolytic plating was used to plate these capsules. Not only the capsules which had the polymer and the metal coating, we also fabricated some capsules which were made of ceramics. Now these capsules had a specific reason. These capsules worked at much higher temperature than our metal coated or polymer coated capsules. Their temperature range is around about 400 degrees C or at most 450 degrees C. But way the direction in which this technology is going is higher temperature, 600 degrees C, 800 degrees C, or no one knows, it may even be 1000 degrees C. The reason is as you go higher in temperature, the efficiency increases. So the efficiency of generating electricity increases. So the target is to go as high temperature as possible. If that's the case, then you cannot use polymer, you cannot use metal because they corrode. So the only material which is left to encapsulate those phase change material which changes their phase, which melts at high temperature, say 800, 900 degrees C, is ceramics. So we have also developed some ceramic capsules. So inside these capsules is the salt. One of the salt which we are using is the common salt, sodium chloride, so which has a melting point of around about 800 degrees C. And I want to emphasize here, sodium chloride as such is benign. We look, it's not corrosive. But when it is present in a solution state, when it is present in a molten state, it is one of the most corrosive material on the earth. So no way you can have a sodium chloride touch with the metal in the presence of air. It's going to corrode it tremendously. But we found out certain ceramic material. It also reacts with many ceramic materials, molten sodium chloride, but we found out certain ceramic materials which do not react with molten sodium chloride. So once we fabricated those capsules, the next step comes is the testing of those capsules, how to test those capsules. The capsules were tested by inserting a thermocouple, and thermocouple is a device which measures the temperature. So there is thermocouple in the middle of the capsules, and there is also a thermocouple at the boundary. So we wanted to see that at what temperature the phase change material melts inside the capsule, how long it takes for the capsules to melt under a certain conditions, and how long it takes the capsules to transfer its heat back to the heat transfer fluid. So all those things needs to be determined in order to further test these capsules. So I will be talking about that. So one of the way, as I showed, there is a thermocouple inside and there is a thermocouple outside, and you heated these capsules in a muffle furnace up to a certain temperature. So starting from room temperature to the temperature 20 degree above its melting point. Now in this graph we didn't show the room temperature, but it's shown from 280 degrees C. So what you see is, as you start heating it up, the rate of increase in temperature is is very, very, very fast. So it increases very fast there. But there comes a point where the rate of increase in temperature becomes slow. It's almost like a flat structure in there. Now that's the time when the material inside the capsule is changing its phase. When the material inside the capsule, it starts melting. So melting, whenever there is a change of phase, it occurs under isothermal conditions. In an ideal environment, whenever material changes its phase, there won't be any change in the temperature. So we actually say the heat is being stored or heat is being taken out under isothermal conditions. So that's the other advantage of the latent heat. When that happens, we can have more useful work done from it. There's the second law of thermodynamics there. So it's better in that aspect also, that the heat is stored or heat is taken out under isothermal conditions. So we know, okay, the melting started somewhere here and it is complete at this point, because at this point again the increase in the temperature is faster than what was happening here. So this window here represents the melting, and this told us, okay, this took around about 22 minutes to melt the salt inside that capsule completely. It's so very essential to know, because when you should be knowing how long it takes to charge a system, and then you should also know how long it takes to completely discharge the system. Remember I said that you need to generate electricity at a certain rate, because all of a sudden there is a demand, so you need to generate that electricity at a certain rate. So you need to know how long it's going to take charge and how long it's going to discharge. So it went up to like 326 degrees C, which was the temperature set on the furnace, and the capsule reached to that temperature, and that's the reason you don't see any change in the temperature in there. That was the furnace temperature. After that, the flow was reversed. That means the temperature of the furnace was decreased. When the temperature of the furnace was decreased, the opposite thing happened. The heat is now being transferred from inside the capsule to the outside heat transfer fluid, which is air in this case. So when that happens, you will see immediately there is a tremendous decrease in the temperature, and the moment it reaches close to its freezing point, you will again see a kind of a plateau there, a flat portion. That's where the liquid phase change materials starts getting converted into a solid. That's where it starts freezing. It's almost similar at the almost similar temperature. There is 1 or 2 degree difference. So it's slightly lower. So that's called subcooling, but it's not that great. It's not that great. So it starts from here. The solidification starts from here, and then it ends up there. It ends up there, and you will see immediately when the whole material got converted into solid, the temperature decreased tremendously. So the solidification time took 29 minutes. So we know that the capsules which we generate takes around about 22 minutes to completely charge and 29 minutes to discharge. And you will see here the solidification is taking longer than the melting, and it's because of the different phenomena involved in the charging and the discharging, in the melting and in the solidification. Now, once we have determined what's the charging and discharging time, we want to test the performance of the capsules over a very long period of time. As I said, once this capsule will be made and this will be put into the storage tank, its life should be like 20 years or probably 30 years, even that. So once you put it, you just forget about it. So you need to do certain accelerated testing to see how these capsules survive the harsh environment of energy storage system. So what we did is we made a number of capsules and tested them at very high temperature, like 326 degrees C. So in the testing, what was done was that the capsules were heated to 326 degrees C, and around about it was kept at 326 degrees C for around about 80 minutes, and then it was allowed to cool to a certain temperature, which is 280 degrees C. They were kept at 280 degrees C for 40 minutes to make sure that all the solid inside, all the liquid inside got converted into a solid. And then when that happens, it was again heated to 326 and kept there for 80 minutes. So this was a cycle, a thermal cycle, which these capsules were subjected to a number of times. So we tested these capsules for more than 2,000 thermal cycles. In fact, what the latest figure is 2,500 cycles. So this cycle which I am shown, these capsules has undergone that many number of thermal cycles. So that gives us the confidence that this is the right material to use as energy storage material in the concentrated solar power plants or any other conventional thermal power plants. So what you see in the beginning, you saw that the capsules were bright in color, but when they were subjected to thermal heating for a number of time, you'll see they turn a little bit of yellowish or brownish. That's because the surface of the metal got converted into oxide. That's what the reaction is. Metal reacts with oxygen at higher temperature to get metal oxide. But once that metal oxide coating is formed, it works as a perfectly corrosion resistance coating, and the metal doesn't corrode beneath it. That's how these capsules have survived so many cycles. So this testing is not only for the coating, the testing is also for the salt inside. See, not only the coatings which are being subjected to heating and the cooling, but also the phase change materials which are subjected to heating and cooling. So whenever you are heating a material, there is always a chance of decomposition. There is always a chance of degradation. When that happens, the materials change its chemical composition. When the material changes its chemical composition, its property changes. Its melting point will change. Its energy density will change. Its latent heat, the delta H, will change. So we wanted to know that what happened to the salt inside the capsule after so many number of cycles. So after passing like 2,000 cycles, we cut open these the capsules, took out the salt, and tested it for its melting point and also the delta H, the latent heat of fusion. And the instrument which was used was the DSC, which is differential scanning colorimeter instrument. And over there, we did it for the as received salt, which was not subjected to heating, and also the salt which was subjected to heating for more than 2,000 times the thermocycling. And what you can see is both the curves perfectly match. So there is no change in the melting point, and there is no change in the latent heat. This is called an exotherm. This is called an endotherm. This happens during the melting, and this happens during the solidification. So there was no change in the phase change material property after 2,000 thermal cycle. That also tells us that the phase change material is perfectly compatible with the storage material. There is no change in its chemical composition. The test which we done initially was on an individual scale, but then we wanted to test it on a large scale in a storage tank. So this system here is built in the lab, and this is a large storage tank inside, and that storage tank contains is perfectly insulated. You are seeing these sheets and also insulating material in there. They are perfectly insulated, and so that there is not much of a thermal loss. And inside the storage tank there are a number of capsules. So the number of capsules which are there, more than 1,000 or so. So there are a large number of capsules inside, and this experimental setup was done at 350 degrees C. And the same thing which we done, we want to see at what how long the system took to completely charge and how long it took to completely discharge. So we monitored the system at different temperature and found out, you will see again it shows the same phenomena. The temperature increases, and then when it's undergoing melting, it flattens up, and then again it increases. And this is the discharging, again the same thing, close to solidification it flattens up and then it decreases. So based upon this, calculations, we could see the performance of the capsules, we could see the charging and discharging time of the system, and most importantly, we could also determine the efficiency of the system, which is close to like 90%, which is a very, very good efficiency as far as the energy storage system is concerned. So this is the technology which we developed, which is fully tested and is ready for commercialization. We are in talk with some companies also regarding this technology. Let's hope everything goes well with there. This is the power plant where it's being tested, and one of the very recent application is that this storage will be used to transport the geothermal energy. There's this place in Europe, it's called Iceland. It has a tremendous amount of geothermal energy available. It uses its geothermal energy resources to meet its energy needs, be it the heating of their room or generating electricity. So they are all generated from the geothermal. Perfectly efficient system and non-polluting system. So it's an amazing system which they have. But there is another island close to Iceland. It's called the Faroe Islands, where they don't have any geothermal energy. So they normally use the fossil fuels, the diesels and all that to get their electricity to meet their energy need. So idea here is to transfer the geothermal energy from Iceland to the Faroe Islands. How you can do it? You can perfectly use the capsules which we have developed to transfer the geothermal energy in the form of heat to the Faroe Islands, and then they can use it for space heating or for generating electricity. The third form of system, the third form of thermal energy storage technology is the thermochemical energy storage. The thermochemical energy storage is the most it has the highest energy storage density. It has the highest storage density. It has a huge potential to store energy. Now, what is the thermochemical energy storage? The thermochemical energy storage is a simple endothermic exothermic reactions, a simple reversible reaction. So if the forward reaction is endothermic in nature, the backward reaction will be exothermic in nature. Perfect that. So a thermochemical energy storage is using a chemical reaction which is reversible in nature to store the heat during daytime and use that heat during nighttime to generate electricity. So this is one of the very beautiful example of how the chemistry can be used, a very simple chemistry can be used to solve our energy related problems. So the process which I'm going to talk about is the Haber-Bosch process. Every one of you know it's so common process where nitrogen reacts with hydrogen to form ammonia in the presence of iron catalyst. The fertilizers we are getting is because of this process, and it's a totally industrialized process, optimized process. Now this same process could be used to generate, to store energy and then later on generate electricity. So what this technology is, what the thermochemical energy storage is that during daytime you use the heat available from the sun to carry out a reaction which is endothermic in nature. So you begin with ammonia and use the heat to decompose ammonia into nitrogen and hydrogen. So this is an endothermic reaction. So you have broken down ammonia into nitrogen and hydrogen. And so that means we have stored heat in the form of a chemical reaction. So thermochemical reaction. During nighttime, when you need the energy to generate electricity, you reverse the reaction. That means you react nitrogen with hydrogen to generate ammonia. And this process is exothermic process. It's an exothermic process. And since it's an exothermic process, heat will be liberated, and that heat liberated can be used to generate electricity. So this is a perfect way of generating, storing energy and then generating electricity. This is what I call the future. This is where the energy storage for thermal energy is concerned is going to go into. This is the least developed energy storage technology. The biggest hurdle is the reversibility of the reaction. The reaction over a period of time, they become less and less reversible. That means, say for example, you converted 100% of ammonia into nitrogen and hydrogen, but when you go in the reversible direction, only probably 90% of that got converted back into ammonia, and certain of those things. So as you keep on doing this process over and over again, the reversible efficiency goes on decreasing. There are other materials also which has even severe problem than that. The second problem with this is how to store nitrogen and hydrogen. So we are talking about a large amount of storage material. So a large amount of nitrogen gas and hydrogen gas. How we are going to store? So that's an issue. Ammonia is a toxic material. So that's the other issue. So people are looking into some other energy storage materials for thermochemical, like the calcium carbonate, which is less toxic. But over there also the issue comes is the reversibility, that as you carry out those reactions, the reversibility efficiency goes on decreasing. So I like to thank some of the persons. Tanveer Alam was my student who was working on it. He's doctorate now. Dr. Yogi Goswami and Dr. Elias Stefnakas, they are the one whom I worked with and are equally part of this project. Dr. Randy Event is our president at Florida Polytechnic University, and Dr. Ghazi Durkazli, he is our provost. So I thank all these persons for making this work possible, and thank you all. If you have any question, do ask me. Thank you very much.